All right, hello everyone. Welcome to my talk. This is called No Heatsinks Allowed, and I wanted to make this generally about low resource devices. I call them little guys, just little weird devices that are everywhere, but sometimes don't get all the attention that more interesting targets do. So a little bit about me. I'm Trey. I'm a security researcher at Crystal Peak Security. We do a lot of work with embedded, fun devices like this. We like hacking around, discovering cool things, making tools. Yeah. So I wanted to start out this talk talking about something completely unrelated to the immediate topic at hand in some ways, but very related in others, which is a trip I took to Seattle a couple of years back. And this is Vetco Electronics. Anyone here been to Seattle? Know what the store is? It's a great store, highly recommend. Inside, there's just a bunch of old devices, anything you want to clutter your home, you can get here. And then it's a virtuous cycle where people buy things and then they go back to Vetco for other people to buy. But it's extremely cool, a lot of cool. This is one of my favorite shots, is just all this old equipment that someone had at one point. That isn't really useful anymore, but is perfect for nerd sniping, people like me. So speaking of getting nerd sniped, I found a weird brown box when I went to Vetco. Promise it's not a bomb. It is very suspicious looking though. And for a long time, I didn't know exactly what it was. I went up to the store owner and I asked him, hey, what is this box? Can you tell me what's going on here? He said, well, it's from a guy who worked in the industry for years. He was clearing out a storage unit. This just happened to be there. We got it. We don't really know what it is. And I told him, okay, I think it's kind of cool. I think it's interesting. How much does it cost? Fully knowing completely well that my wife already had completely stuffed suitcases. And TSA would be a little bit nonplussed to see this coming through. And he said, well, pay whatever, what do you think it costs? What do you want to pay? And I said, $20, and he said, you got a deal. And that's how I paid $20 for what ended up being the worst piece of networking equipment I own. So if you take a look at the front here, this is a modem. I don't know if you've used dial-up modems. People don't have any reason to nowadays, but it's got all these fun blinking lights on the bottom and then a couple of manual switches along with the on-off switch. And it's just, someone obviously built this themselves when they were testing things out, and it made its way into my hands. And then I promptly flew home and did nothing with it for a full year. Went to my junk drawer. So this is a talk about what's in your junk drawer. These weird little devices like this, stuff that's interesting, maybe you just don't have time to actually work on or really dig into like you have to. And I think there's so many devices like this out there where they could be really cool if only we had the time to actually look into them properly. And the background knowledge. A lot of these things, I'd worked with dial-up modems before, so I knew the basics of how to get this going, especially like weird, slightly older tech like this. But there's a lot of initial knowledge required to take all these things in our junk drawer that could be cool projects and then make them into something actually interesting. So today I'm going to talk about three things. The first thing is a really cool conference I went to, workshop actually, called Low Resource Computing. The second one, I want to hone in a little bit and talk about the taxonomy of what I would call low resource devices. And then at the end, we'll have a special mystery guest device. So for part one, low resource computing, this was, let me pull up my slide here. So this was a year later. I got an email about this workshop that said, bring any device you want. We're working on embedded devices, weird little things. Just it's a space where I could take that time to take the stuff in my junk drawer and at least do a show and tell, if not actually do something cool with it. So the email actually said, I'll read it out here, feel free to bring any low resource hardware or software that excites you, quirky retro gear, half-working prototypes, and analog tech. And it seemed perfect, seemed like a fun time. So I packed up and I headed to Dartmouth, of all places. Here's the website. And they say you can take a plane to get to Dartmouth. I would not recommend that. I didn't realize this is what I was signing up for when I bought the ticket, and then by the time I got to the airport, it was too late, and it was non-refundable. So this was the first time I've experienced pitch and roll on flights before. This was the first time I felt yaw, and that was not something I would recommend. And so we were presented with this scenario at the start of the conference, which was, again, there's so much nerd sniping in this talk, but this was like a cold start to society. Say all the internet goes down. You have only yourself to rely on. You've got to start connecting devices. You've got to start talking to people, setting up networks. How would you do that? And in my developer brain, I'm like, great, I get to refactor society, technology exactly as simple as it needs to be, and nothing more complex, nothing more bloated, none of these like crazy BGP things I don't understand. And so that was the start to this conference, and people ended up building some really cool things and taking some time to hack on fun devices, like the email said. So like a Game Boy repair and programming, PDA browser exploits, that was really cool. LoRa mesh networking, and I wanted to set up a dial-up backbone, being the guy with the weird brown box I brought to the conference. So this is what I ended up with. This is not that interesting, but I love long chains of technology together. So from a CCTV camera, IP CCTV camera, to an iMac G4 through a switch, to a modem, to a PBX, to another modem, and then to a recipient computer. So someone can pull frames from this IP camera through this primitive network I set up. And here's one of those frames. This is presented in its full glory, 2 bits per pixel PNG image. Gives you 4 shades of gray. And I went ahead and redacted people's faces so you couldn't recognize them. That was mostly a joke. But we ended up getting this working, and that was kind of, it always takes longer than you think it will, right? So I spent 2 full days hacking on this, just trying to get it going. But again, that's how it is working with the stuff in your junk drawer. There's a reason it's in there. It went at a blazing 15 seconds per frame, and was not the grand vision I wanted for it, but I did get to open up the dial-up modem here, and we'll come back to this later, but there's actually a chip. You don't really see this as much nowadays, but it's this gold chip you can see in the upper right. And that is, as far as I can tell, it might be the first fully integrated modem integrated circuit in this little test card that someone had put together for their dial-up communications. And it took me forever to get this thing working. I actually could not talk to it for the longest time, but then it took me even longer to figure out that it doesn't support the AT command set. This predates AT commands for modems. So it doesn't even have a dialer. You just have to hook it up to something, and then there's an answer button that you can press to receive a call. But it's 600 baud, which is not 300 baud. And it's this old modem from the 70s. It's 50 years old. So this is, some pretty cool tech that's been around for a hot minute here. But I don't know, I thought it was really cool. It ended up just this random device I bought from Vetco in Seattle. I ended up having it be useful in this long chain of CCTV to recipient at low resource computing. So that got me thinking, like, what's the minimum viable modem? Because there is no AT, there is no dialer. It can answer calls, but you have to press a button. But I was able to send video. I was able to transfer data. So this is getting into part 2 of this talk, which is low resource devices, things that are constrained in many different ways. Again, pulling things from my junk drawer, I'm going to call out a couple of devices here that I thought were interesting. So talking about memory constraints, everyone knows, that's the wrong slide. This one. The Game Boy has 8 kilobytes of memory. Every byte is a decision in here. I was talking to a coworker recently, Anthony here, who about this, and for the demo you'll see later, I told them, what do you think, I'm megabytes? You know, like this is, it's very constrained. And so every byte is a decision. Everything that you're working with on this has to be optimized. There's no waste, there's no loading up Chrome to display the game. You know, you have to work with the hardware and really get close to it to make something interesting and work. And if you look at the Game Boy demo scene, people have done exactly that. And one other thing I wanted to touch on here is that constraints often come in groups. So the Game Boy is constrained in working memory, it's also constrained in power. Really, it's a feat of engineering for this to be such a small portable game console at the time. Next constraint is storage. So this is, I have this with me. This is an Apple QuickTake 150. It is a early digital camera, and it can store a whopping 16 images on it, which I don't know why you would actually use this, but it's pretty cool. And it's a little device that at the time was pretty groundbreaking, but the technology was not there to allow you to store a lot of things on it. And so the constraint sort of drives consumer, or not consumer, but the end user's behavior. And that's been talked about to death with cameras of like, oh, you can take 1 million photos nowadays. But in this case, it really shaped your behavior for how you work with this device. Next constraint is size. So a lot of these devices that I'm talking about today, there's like a fun demo scene around, and there's a fun modding community around because they're cool, because people like working with constrained things. It's part of the reason why people write poetry, right? You have to work within a framework and a number of constraints. And so I have a iPod at home, a video iPod I got when I was 13, and I still use it now. And the only reason for that is that I no longer have to work with, let me take this out here, show and tell, this tiny mechanical hard drive. This is a full hard drive that they shrunk down to fit inside of the iPod. And it's just a feat of engineering because it's spinning metal in here. And so you think about this, you're walking around and you've got this in your pocket, and it's extremely small, but it's got a full, I don't know, this is incredible engineering. Full size, or not full size, but fully capable hard drive inside of it. Now in terms of power, I want to call back to LoRa, which was one of the things that people played around with a lot at limited resource computing. Really cool technology in terms of sipping power, but still being able to send data. So there's a lot of smart utility meters that are being rolled out with this. So something to keep an eye out for if you're interested in LoRa hacking. Also, they're used in agriculture all the time. So anywhere where you have very little power available for your device, these will be very useful. But it was cool because people used this at the conference, and I meant to mention this earlier, but one thing that I wanted to do was have this CCTV camera. It was a part of a chain where I wanted people to be able to play Twitch Plays Pokemon, but with our limited devices. So people could send commands over LoRa, and then you see the frame, which is transmitted from the CCTV camera pointing at the Game Boy. And there was a guy there, Michael, who had his Game Boy and then was soldering to it. And we never got it to work on time, but that was the grand vision for why that existed. And I had a hard time coming up with this sort of constraint here because I think it is a constrained device, but I couldn't think of a name for it, which is awfully ironic given what I put on the slide. And this is in terms of like expressiveness. So if you think about the instruction count on x86 64, if anyone could give me a guess how many instructions there are on this architecture. You're in the range. Exactly. It's over 1,000, somewhere between 1,000 and 3,500, depending on how you count. But it's incredible. No one's ever going to learn all of this. This is the reason we have compilers. But it's crazy complexity. But it's very expressive. If you have one specific problem, you have one specific pre-made solution for it. But how low can you go with instruction sets? AVR actually has 120, which is higher than I was thinking. The classic brainfuck has 8, and then there's also the concept of a one instruction set computer, which is Turing complete, but not something you'd ever actually want to work with. But speaking of things you don't want to work with, this is, let's see if I can get the cursor here. This is a brainfuck CPU I built by hand using 7400 series logic gates put together. And so if you constrain some things, it makes things possible. I would never be able to create a CPU that has 1,000 instructions, but it's actually relatively doable to get a CPU working within a few hundred hours of hand wiring and have it go. So I built this when I was in Seattle. It uses a PS2 keyboard. It's super easy to read outputs from that, and then it's just running cat right now, but it translates the key press into a command for the display. So 8 symbols, the rest is convenience. Really 1 symbol is all you need, but I draw the line at 8. Final thing I want to talk about here is cost. So much of what we have around us is driven by cost, but the classic examples are like, how cheap can we make a microcontroller? How cheap can we make something that connects to the internet? So an ESP8266 is extremely cheap, but very capable. And we have CPUs nowadays that are so cheap that they're disposable. We put them in everything. And this is the other. Give me a moment to find my show and tell for the class here. This is some strange crypto I bought years ago. That is a physical bill that contains cryptocurrency inside of a secure element on the Flex PCB. And it's beautiful. I think it's great. The value plummeted. These are worth nothing. But it's pretty cool. And I think it's an interesting concept. And I don't know if they knew that they set out to make the perfect nerd snipe material on Twitter, but when I saw this. But it's pretty cool. And these are basically a smart card. Yeah, it has a secure element in there. You can trade this physical crypto. I don't know why you would, but it's interesting. And it's a smart card disguised as a dollar bill. And speaking of, it's time for part 3, our mystery guest device. It's a smart card, and there's between 30 and 50 billion of them in the world today, which is a staggering number, and I don't know who exactly counted every single one of them, but it's a huge number of devices, and they're all around us. Every single one of you right now has a smart card in your pocket. Your credit card is a smart card. And in fact, your credit card probably runs Java, which is mind-blowing. When I first found out about that, it just did not compute, because how does such a constrained device run Java? Before we get into that, let's talk about what a smart card is. You've got your microprocessor, your memory, and then some basic communication, contact pads. The microprocessors in them are often undocumented, rarely. I haven't been able to find any information on these, just scouring the internet, just general data sheets like you would get for other parts, other devices. They're super constrained in terms of memory, kilobytes. So why are they running Java? And I think a lot of it comes down to the timing, is that Visa and some other networks wanted to standardize on a common platform in the mid-90s, which is peak Java craze time. So some mad lad said, let's put Java on them, and then everyone can just write Java, and we can just have Java on credit cards. And that ended up being the standard. So that's how we ended up with a super basic Java virtual machine on every credit card. And I think it's Java 1.7. It's a little bit stripped down. There's no floats. Obviously, a desktop application is not going to translate well to a device with 2 kilobytes of RAM, so there's some specific things that you have to do. And one of the strange things about these cards is that they have RAM, but by default, every object, every allocation goes into persistent storage. And that's extremely slow if you're updating things, if you're working with this card. And we can skip through this, but yeah, like I said, everything, it's like if every object you created in Python or Java was just allocated onto a USB drive. So there's this concept of transient arrays that exist within Java card, and we'll touch on that in a bit later. I haven't found too many people who look too much into Java card. These guys are pretty cool. They have a website where they compare a number of different cards. They have some profiling they do. They do differential analysis on like timing between different cards so that you can tell roughly which ones have a similar CPU architecture because these are so niche and complex. But they were a good resource for getting started with this. So I wanted to start working with smart cards, and I ended up running through this website, trying a couple of things, trying to acquire some. They sell them really marked up on Amazon. You can get basic ones for fairly cheap at wholesale prices, but if you're a hobbyist and you just want to play around, it's surprisingly expensive, about $5 per card, which in the grand scheme of things is not that expensive, but when it's kilobytes of RAM, it is. So I started by creating a few applets for my smart card. And I wanted to think about how far I could push it. In fact, I wanted to try running some demos, running some games on a smart card. So how far could I push this? And I asked myself that question, and that's how I ended up writing a compiler. I didn't set out to do this, but the reasons that this exists was again, I started writing Java for Java cards. I wanted this thing called a transient array, which is really just a view into memory and RAM. So you have to request an allocation of a byte array in Java, and then you get some sequence of bytes back. But then you want to start putting a ton of variables in this byte array. So you start doing indexing into it and declaring constants. And so then I started writing preprocessor macros to declare what the constants are. And then I wanted actually to put structures in there as well. And then nested arrays, and I wanted control over how allocation is done. And then I wrote a compiler. So JCC is a C2 Java card bytecode compiler. So one of the things that I use inside of JCC is converting arrays of structures into structures of arrays. So they have native data types for bytes, shorts, and integers. One of the fun things about working with Java is that there is no unsigned type. Everything is signed. So if you need to port something which uses unsigned comparison, you'll have a lot of very subtle bugs that pop up in strange ways. But they have this 3 different array types, bytes, shorts, and integers. So inside of the compiler, I manually take all of your statically allocated data and then assign indexes based off the data type, and then everything just works. So like I said, it's static allocation. There's no memory allocation. There's no recursion allowed because I wanted to make sure that as you're running this, you don't hit a stack overflow. And it's been fairly helpful for porting games and little demos to it. Like I said, it's fairly constrained. There's no malloc, recursion. There's no floats, unsigned, unions. But the basics are all there. So you can get a workable C demo ported to Java card. And I'm releasing JCC today. You can hit the GitHub if you want to look into it. You can start compiling. It's got instructions. The whole goal of this was to make it very accessible for writing performant, weird applications for smart cards. There's a lot of tutorials on just writing Java for smart cards, but I wanted to make it so that you could greatly increase your performance. Because again, those transient arrays are really such a boon to performance. So, that said, I have a few demos I'd like to launch into. This is going to be hard. Give me one moment. So, for the first demo, thank the demo gods. Okay. No smart card inserted. Okay. There it is. So we have 2048 running on this smart card. I haven't hooked up the RNG yet, so it's the same sequence every time. I've gotten pretty good at it. But 2048, you can run games on this. And just worth explaining here because everything you're seeing inside of the inner border is fully rendered on the card. So it's, like I showed you in that 2 bits per pixel image earlier, this is actually a 4 bits per pixel image that's returned and then just blitted straight back using a driver Python script I wrote. And so it's a request response architecture. So I make a request that contains the keystrokes and then I get a response back, which is the frame buffer. So a very, very simple, minimal sort of interaction here. Everything's being done on the card. So let's do one more. Here's a Flappy Bird on a smart card.
You have to make the frame smaller, dude?
Yeah, so one thing that's worth noting is that there's the smart card and then there's the simulator. So for a lot of the dev time, I was working in the simulator, which is about 80 times faster than the smart card. So I thought I was doing really well. And then when it came to porting time, it's a little bit slower. So this is 1 bit per pixel, on or off, and then I had to constrain it because if you think about it, and you think about working with constraints, 2048 does not have a constraint of being near real time, you know? It is very slow, it's not an interactive game. It is an interactive game, but it's not based off of interaction with time. It is just, you make a move, that's what happens. So with the time element, I shrunk it down so it could be a little bit faster. A lot of the rendering time is spent just turning pixels on and off. You can make that a lot faster with built-ins for that exit the JVM and then do stuff in whatever weird native architecture is on this device and then go back. But yeah, it's at 20 frames per second and it's serviceable. Let me pull this up. So the next demo, speaking of wanting to do Twitch Plays Pokemon, this is my own smart card Pokemon. Hopefully Nintendo doesn't mind too much. So you can, I didn't get to make it, thank you. I didn't get to make this for the con, but I thought I would call back to my dream at the limited resource, or low resource computing and demo Pokemon here. For the final one, let's see if this works. Uh-oh. I have to change the card.
You need to take the card.
This is my other card.
Blue key or the...
Excellent. And here we go. This is E1M1 rendering at 1 frame per second on a smart card. So if you played Doom, you should recognize the geometry. But I did so many hacks for this. The trig is all wrong. The division's an approximation, but it sometimes hits 2 frames per second. So I take that as an absolute win. But this is Doom on the smart card. Yeah. Thank you. Thank you. So there are no floats, but I mean, Doom is smart about how it does things, and it doesn't rely on an FPU. It uses fixed point integers, not instead of floating point. So if you want to see it at full speed, here it is in the simulator. So if I had a faster card, this is how the demo would look. But yeah, there are high-performance smart cards out there, believe it or not. They just don't give them to me. You could. Yeah, exactly.
Distributed computing.
Yeah. All right, one more demo, and then that would be good. Wrong card. Sorry, this one's declined.
Oh my gosh.
So you might recognize this. This is Bad Apple running on a smart card. But yeah, that's those are the demos. So again, the reason I talked about transient arrays a lot, and none of this would have been possible at any reasonable speed unless there was all this tooling around making sure that memory and allocations actually go to RAM instead of being persisted. So it makes translating C code workable. So just to kind of wrap up here, look through your junk drawer, think about the cool devices in there, try and make some time to actually dig into them and learn all the infrastructure, all the setup, everything you have to do to start working with them and interfacing with them, and see what you can build, because I think this is one of the cool things about cybersecurity and hacking is that these devices that seem inaccessible are things that we can access with enough time and effort and just banging your head against the wall to get them working. So take a look in the junk drawer, pick one device, see how far you can take it. And if you're ever in Seattle, stop by Vetco. They'll give you a lot of things for projects like this. One more thing before I go. I have a special card I would like you all to see. Just find my window here. That's my talk. Thank you. It will keep going. Okay. Yeah. All right. Yeah, let's do some questions. If you ask a good question, I will make you a smart card with any of these demos you want on it.
Can you repeat the questions too?
Yeah. Start here. Yeah.
How, like, start to finish, how long did it take you to make K16?
Start to finish. Gosh, so that's tough because I spent a lot of time just learning the background information. So that's sort of the infrastructure I was talking about that I was building up to where I could actually work on JCC. It probably was over the course of not that far off of the actual CPU I built. So probably about 100, 150 hours of work. And it's not like a great compiler. It's written in Python, you know? It doesn't have to be that good though. And it has to generate Java bytecode fairly efficiently. So there's some people optimization and basic things it does, but nothing insane other than, again, moving to transient arrays instead of the default allocation method for things.
You mentioned we all have smart cards. Do they all have the same like connectivity? Like if I hand you a smart card, you can just start talking to it?
That is a standard. So the question was smart card connectivity. Can everything just talk to the same smart card? Pretty much, and that's something I wanted to include in this talk, but there's pinouts you can look up for smart cards. It's fairly simple protocol-wise. Yeah, so you cannot, for example, load applets onto your credit card. You know, these are meant to be secure devices, so you have to specifically buy open devices to do things like this. But generally speaking, the platform is standardized. That's that global platform that I was talking about when some guy, you know, said, let's put Java on credit cards. I think in the back you had your hand up for a while.
So awesome talk. A few things. One, have you tried, loading some code onto the card that will, have you looked closely at the system that like payment machines actually use to communicate with the card? And if so, have you tried like fuzzing that or?
Yeah, so that was something I looked into for this talk. There are a lot of people who have, not a lot of people, but there's been talks at DEF CON about the actual terminal devices like you'd see in a store. And people got Doom running on those much more efficiently than on the card itself. One of the dream demos I would have is running Doom on the smart card, but displaying on the handheld payment terminal. So if anyone wants to help with that, let me know. But yes, the payment terminals themselves, I have not looked too much into. I've previously done work on ATMs. So that was another device that has run Doom that I've worked on. We created a CTF at a company I previously worked at for ATMs. But overall, the sector is really interesting to look at because everyone's got a credit card, everyone's got a smart card at home, and you know, working with financial, physical devices like this is interesting. Right here.
So credit cards one thing, but like PIP and CAT cards, identity cards, those sorts of
It's all the same protocol-wise. So the question was like PIP and CAT cards. Is that just what you're asking about, is whether they're the same?
Yeah, I mean, are they different? Do they have more capacity? Ultimately, what can you do with it?
Generally speaking, I mean, nobody tells me exactly what's a CAT card is running under the hood, but these are all the same mechanism. So it's all smart cards, you know. Ultimately, what I have here could technically be a credit card, or it could be something you use for authentication, like a CAT card. It's all the same. Not exactly the same, but broadly speaking, the physical interface, at least, is the same. And again, I don't know what CAT cards run, but if I was a betting man, I would say something it's running something compatible with global platform, which is what we have for this.
I mean, it's big enough to store the privacy. So.
Yeah. I mean, so memory-wise, these things have about 4 kilobytes of RAM. This one has 4 kilobytes of RAM and somewhere in the range of like 40 kilobytes of flash, ROM, something like that. In the back.
What hack are you most proud of to get all of this running?
The question is, what hack am I most proud of to get all of this running? I think it's the magic that's done in the compiler, I think, to actually speed this up. So at various points, I added some optimization passes and integrated some of the Java native stuff. So I hooked up your C runtime memset call to some native code that gets called typically under the hood when you do like a util method for setting arrays and things like that. So that, just the performance optimization, I think, was the coolest part. Right here.
So what about considered some, I guess, ways to make the input more independent, not to have a smart card like them to see?
Yes. Originally, when I was suffering from crazy scope creep for this talk, I wanted to, the question was, have I considered making it not just be on the PC? I wanted to have a Game Boy, and I drew up a circuit diagram for this and figure out how all the components fit together, but something with a screen and a smart card reader IC, and then the smart card, in its response, speaks the native protocol of the screen that's attached. So you just wire that output directly to the screen, and then you can display frames that way. So my dream is essentially, it's a Game Boy, but the CPU is on the cartridge itself, and everything's on the cartridge itself. The handheld would just be the smart card reader, and then some glue logic to hook it up to the screen. So maybe in a future talk. Any other questions?
Do you have any sense of like what the native architectures of these cards is? Is that a consistent architecture, or is there some?
The question is whether I know the native architecture of these things. And that's something that, so the JC AlgTest people that I mentioned, that you should look into their website. That's why I was talking about their differential analysis on performance. So they're using performance as a side channel to kind of measure how something is implemented. And then from that, they can correlate to different CPU architectures. But ultimately, again, these are not open devices. Right here.
Next year you're going to do the .NET version?
You know, I've got the Windows 2000 jacket here, so who's to say? Maybe I will do the .NET version next year. All right, final question?
Did you have to do any kind of like driver modification to read or write to the card? And I'm asking because like, I guess it seems like it could be potentially used as a sort of like mass storage device that wouldn't normally appear like a mass storage device on a system, because you know, you're not plugging in a flash drive, you're just plugging in a smart card that the system might already be ready to recognize and potentially could ship malicious code that way.
That's interesting. I don't know driver side how all of this works, so the question was whether I had to do any sort of driver modification, and you know, how, can you clarify what you mean by malicious devices?
So, like, it's a common security control, right? You don't want to allow mass removal
Oh, sure.
devices right from the system, but, you know, in some areas, smart card reader might be a common thing that's accepted. So, you know, if you can read
Yeah.
from the card,
I see.
that might be a way to...
I see what you're saying. So in secured spaces, you're not allowed to bring mutable memory in. Except your ID badge, except it's like your credit card. If it's done right, it should not be mutable, right? But you can't tell just by looking at it, I guess, is one thing to consider. All right, y'all have fun with that one. All right, thank you.